Hello and welcome to the Verilog FPGA project number 5, Blinky LED. Let's have a quick project overview. In part 1 of this project, we are going to design in Verilog a parameterizable Blinky LED module. You are going to be able to change the input clock frequency, the output LED frequency, and the number of LEDs. Next, we are going to create a Verilog test bench for the Blinky LED module. In the end, we are going to create a Modelsim project and perform a simulation. On the FPGA board, the project will work in the following manner. We are using the DE1 SoC clock 0 that has a frequency of 50 MHz. The circuit starts working only if reset N is set to a logic 1. After this, the configured number of LEDs will toggle with the default frequency of 2 Hz. This Verilog module is a clock divider that allows you to generate low frequencies between 1 and 20 Hz that can be observed on an LED. You can change the parameters of this module depending on your development board, and you need to have at least one switch and one LED. Even if you don't have a development board, you can watch this cool project and do a Modelsim simulation. In part 2 of this project, we are going to create a Quartus project, synthesize the top module, connect the design to the FPGA pins, and in the end program the DE1 SoC board and do a small demonstration. In this part, we are going to see how our Verilog code from part 1 is translated by the Intel Quartus synthesis tool into the circuit below. The DE1 SoC board will behave in the same way that you see here. If you're a complete beginner or you are not familiar with Intel Quartus or Modelsim, I recommend you watching any of the tutorials below. Switches to LEDs, multiplexer to LEDs, or binary adder to 7-segment display. These can be found in the project description. And now it's action time! Let's analyze the top-level port description for the Blinky LED module. This module has the following parameters. The clock frequency parameter, it has a default value of 50 MHz. You should change this according to your FPGA board clock. The LED frequency parameter has a 2 Hz default value. The bus width parameter has a default value of 4 and represents the width of the output bus. The ports of this module are the following. The clock port is a 1-bit input port for the clock. Reset N is a 1-bit input for an asynchronous reset signal which is active low. OLED is an N-bit output port which is connected with the LEDs. Please create the following Verilog files: blinkyled.v and tb-blinkyled.v. The full project can be downloaded from ovisign.com/courses. Let's analyze now the content of blinkyled.v. The Blinky LED module is basically a counter that counts clock cycles depending on the ratio between the input clock frequency and the output LED frequency. If your development board has a different clock frequency or you want to have a different toggle frequency for the output LEDs, then you need to change the parameters according to your settings. I use a value of 50 millions because I have a clock frequency of 50 MHz. Verilog allows you to add underscores between the digits of a number to have more clarity. Depending on the values you set for the parameters, you will get a hardware circuit that has a particular size. This is how parameters are used in Verilog to describe versatile circuits that can be synthesized depending on your system specifications. At line 34, we declare the module ports, which are clock, reset N, and the OLED output. The Verilog code from lines 39 to 52 is executed only at compile time and calculates the width and the maximum value for our counter in order to obtain the LED blinking frequency. This code can be used in other projects where you need to calculate the base 2 logarithm for a value or to ceil a ratio between two parameters. Although Verilog has the $log2 and the $ceil functions, they are not synthesizable. That's why we need to implement our own versions. At line 50, we declare a local parameter that gets the sealed value of the ratio between the clock frequency and the LED frequency. Local params cannot be changed from outside the Verilog module, while parameters can be changed. At line 51, we calculate the number of bits our counter needs by computing the base 2 logarithm of the freq ratio parameter. The local param from line 52 is used to clear the value of our counter at half the value of the frequency ratio. We subtract 1 because our counter starts from 0, and if we had a maximum value of 100, then we need to count from 0 to 99. Starting from line 55, we have the Verilog code that is going to execute during the simulation time and create our hardware circuit in the end. The reg variables from line 56 and 57 are used to create the flip-flops necessary for the counters and for the output LEDs. At line 59, we create a comparator that will be used to clear the value of our counter when the counter register equals the max value. At line 63, we create the counter sequential circuit that will clear when reset n equals 0 or when the counter reaches the maximum value. If neither of these conditions is met, then the counter will increment with 1. At line 73, we create the output flip-flops used to toggle the LEDs when the counter max value is reached. In the end, we connect the OLED output port with the LED register using a continuous assignment. In part 2 of this video, you will see how this circuit gets synthesized using Cyclone 5 FPGA logic elements. If you want to easily master Verilog for FPGA or ASIC design and verification, I gladly recommend you my course, Verilog HDL Fundamentals for Digital Design and Verification. Let's analyze our test bench now. We first declare the timescale. After this, we have the test bench name. From line 21, we declare the test bench variables. We use the reg type for the input ports of our DUT and the wire type for the output ports. These three parameters are going to be connected with the parameters used by the DUT. This parameter is used to express how many nanoseconds a second has. The next parameter represents the half of the period of a 50 MHz clock. A frequency of 4 Hz means that we should see 4 complete periods on OLED during 1 second. Here we create a 50 MHz clock. This initial procedure is used to create a simple test scenario. First we clear the reset, we wait for 5 clocks, and then we set reset n to 1. From this point on, our DUT should start working. Line 57 means that our test bench should wait 1 second and 1 posage of OLED. After this, in 100 nanoseconds, the test bench stops. This should be more than enough for us to see that during 1 second we have the right amount of toggles on OLED. Let's create a new Modelsim project now. We use the same project structure that we used during the rest of our course. We open Modelsim now. After you create the project and start the simulation of the test bench, please add all the internal signals from the DUT inside the wave. If you don't know how to do this, please watch project 1, 2, or 3. Since we use a clock frequency of 50 MHz and we want to simulate more than 1 second, our simulation time will be extremely high. As you can see, the simulation in this case could take tens of seconds or even minutes. After this finishes, I'm going to show you a way to make the simulation 1000 times faster. If we expand OLED, we're going to see these signals. These are going to make the LEDs blink 4 times in 1 second. Let's measure the period of the OLED signal. For this we need 2 cursors. We add another one from here. We move it close to an edge and then select this signal and find next transition. Now we select this, put it before the edge and select Find Next Transition. After you place the cursors, you can see that between them we have a difference of exactly 1/4 of a second. This shows us that we correctly calculate our timings using our Blinky LED circuit. If you wonder why you see only 4 pause edges and not the 5th one, let's zoom in the end of the simulation. You can't see the 5th edge because this part of the simulation represents a time slice very small compared to the time consumed by the simulation. Let's see now how we can change the simulation to consume less time. We go in the test bench again, and here we write a 6. This decreased 1000 times the 1 second time slot, meaning we are simulating now 1 millisecond. Now we click on project. You can see that we have this question mark here. Right click, compile, compile all. Left click here, restart, and click OK. Now you click run all again. The OLED behaves the same, but the simulation time is 1000 times smaller than previous. As you can see now, all the parameters are scaled down, and even the length of the counter is decreased. Now I invite you to analyze a little bit how the counter and OLED behave during the simulation. After this, let's do part 2 where we implement the circuit on the FPGA. Have fun! If you like this video, please press the like button and subscribe. If you like this tutorial and you're interested in an easy path for learning Verilog for FPGA or ASIC design and verification, I gladly recommend you my course Verilog HDL Fundamentals for Digital Design and Verification. You can find the link in the video description. For more tutorials and support, you can join our Facebook community. Your strong Verilog foundation is only one click away.